recording. Hopefully today we won't have any killer spiders to worry about.
Yeah, I should be all right today.
Should be all right. That's good. All right. All right. So I'm going to jump into this. Let's go to. All right. So takes it a second. All right. And let me go to. Oh boy. Being slow here. There we go. Duplicate. Okay. All right. So we started talking about differential equations. We got more to say about it. I know you guys have been exposed to differential equations probably at least twice. You've taken differential equations, right? You've seen it in circuits, hopefully. I know Yahoo is doing it in circuits too. I don't know what they do in circuits 1, right? But Yahoo kind of jumps to the way Yahoo and I do this, he kind of jumps to the solution. So I'm kind of going through the process of how you get to the solution, all right? That's really what our focus is here. So last time we talked about first order. Today I'm going to introduce second order, and we're going to start talking about second order and go through an example today, and then start doing some more examples on Thursday. And we're going to start also on Thursday this numeric solution idea, all right? One thing I wanted to point out, you have homework 4 due this Friday. Homework 5 will be next week. The other thing that'll be coming out next week will be the first project, all right? Which is also 13% of your grade. All right, so we'll have more to say about that Tuesday next week, but I expect that project to come out at the end of next week. Okay, all right, so we'll have plenty to say about that. That project's going to get pretty MATLAB intensive, but it's going to be a lot of example sort of things, real world problems that you're going to deal with. Okay, we'll talk more about that as that approaches. All right, so last time we talked about this idea of what I call a non-homogeneous differential equation with constant coefficients, a mouthful of words for sure, right? But the key thing to that expression is what we have is these are my constant coefficients, and I said this guy has an order n, right? The order is equal to the number of derivatives that I have, and I tried to give that in kind of a general context last time. You know, you guys worry about grades and due dates. I don't know what the due date is. I know when it's coming out for now, but I'm not sure quite about the due date. It's a good question. We'll talk about that next week. It's going to be, you know, somebody wrote 1020 in there. I don't know if that's true or not. We'll talk more about that when it's posted. Okay, but it'll probably be on the order of about two to 2.5 weeks is my expectation on that. Okay. It's a good question, but I'm not quite ready to answer it. I should have expected you guys to ask me that though. All right. Anyway, let me keep going with this. Last time I talked about the order of the equation is equal to the highest derivative I have, right? So if I have a second order system, the highest derivative I have is the second derivative. Just intuitively, I started talking about this a little bit, where intuitively what I sort of said was, if I have an expression that, or if I have a system that has an energy storage element, that's what causes me to have a differential equation, right? So if I have one energy storage element, what order equation am I going to have? First, all right? If I have a second order system, I have 2 energy storage elements, okay? Today, we're going to get into second order systems. When I have second order systems, you can get strange behaviors that begin to happen. Okay. All right. So then I guess the other question is, I said my solution always has to it both a steady state component and a transient component, right? The transient component always has what form? Well, so in general, my solution is always what kind of function? Exponential, always exponential. And if I have a first order system, how many exponentials do I have? 1. If I have a second order system, how many exponentials do I have? 2. All right. Now you learn in circuits basically these sort of ugly, goofy formulas, right, that have sines and cosines and stuff like that. I'm just going to keep it as exponentials because now we're ready to say all sine and cosine is what? Complex exponentials. All right. And I can keep them in that form. All right. We're going to do an example of that here today. All right. So a couple of things I wanted to touch on real quick before I get too far into this. I mentioned last time this thing called the unit step. And you guys didn't seem to be familiar with the unit step. So I wanted to kind of touch on that guy again. All right. And I'm going to define it like this: t greater than or equal to 0. All right. The unit step is this function that I have shown right here. All right. So unit step, u of t is what we call it. It jumps from 0 to 1 at time t equal to 0. So the way mathematically I would define that, I would say u of t is equal to 1 for t greater than or equal to 0 or 0 otherwise. Okay. Now why do we make use of that thing? Well, let's say, for instance, so classic thing that you might see with Yahoo, right? So I've got this circuit here in the bottom, right? So I got a voltage source, and let's say this guy is, 5 volts. Okay. So I got a 5-volt source. And then typically with Yahoo, right, in circuits 2, you guys will say, well, I closed that switch at t equal to 0, right? So if I looked at the voltage, and I could do a KVL around the loop right here that includes the 5 volts and that Vs. And I could do it. So I could say, what's the voltage V sub S, right? If I looked at the voltage V sub S as a function of time, what would it look like? Yep, it would be 0 and then it would become 5. So in this case, I'll write this guy instead as this would be Vs of t. All right. And this would be 5 volts. Okay. So I could say that I have, in this case, Vs of t equal to 5 u of t. All right. So it's a way of representing the physical system. I'm modeling the physical system with this mathematical function. All right. So not a huge deal, but it's helpful to me. So we'll use that function u of t a lot. All right. So the other day, what we considered is what happens if I have a sinusoidal input. And again, I said I put a video up, a separate video, completely separate video that walks through an example of a first order system with a sine wave input. You'll want that for problem 2. All right. When I look at this, the real thing is I typically say that my input is cosine omega naught t times u of t. So the fact that I have the multiply by u of t means what? Well, it's basically the same thing as if I had here a cosine omega naught t like that, and then at t equal to 0, I close the switch. All right. And what is that representing? That's representing pressing the on button, right? Or turning this thing on. That's all it is doing, is representing it mathematically. And what it would look like is what I've drawn down here. So it's something that's 0 until time t equals 0, and then it jumps up and becomes cosine. Usually what we do in all of our analysis is we do all the analysis for t greater than 0, and we've just dropped the u of t. All right. So anyway, nothing too fancy there, but I just wanted to talk about that. We're going to use it here as we go. All right. Now, the thing I talked about, and the homework is set up in this way. So we're going to look at some examples like the homework here. So basically, I give you 3 steps. Okay. Step 1 is to solve the homogeneous equation. Okay. So the homogeneous equation is what? When I say the homogeneous equation, what do I mean? What is different?
Equal to 0?
Set it equal to 0, right? And I'm going to stay consistent with the book. They call that the complementary solution, y sub c. So I call it y sub c throughout all my stuff. The non-homogeneous equation is just the equation, all right? It's whatever I was given originally. The solution to that guy is what I call the steady state solution, or the particular solution. And we use something called undetermined coefficients to do that. All right, so we're going to talk about that method some more. All right, our solution to that guy is called y sub p, and then the final solution, the total solution I call it, is basically combining those two. And it's with the combination of those two that I solve for my initial conditions. Okay. All right, so we're going to look at an example. All right, so here is a circuit where I've got x of t equals 4 times u of t. All right, so I've got this. Again, I'm being mathy on this, right? I'm basically saying that my input is called X. My output is from that picture, it looks like it's the capacitor voltage. I'm just calling it Y, but it's my output, Y, is the capacitor voltage. And so I don't know what the value of R and C are in this case, but this isn't circuit, so I don't really care. What I have is this equation right here, and I've been told that my final value, or my initial value, sorry, is 10. Okay? So before I go any further and try to solve this thing, and I want to go through the steps and try to solve this guy, let me ask you right now, what is the final answer going to be? What's it going to look like? You may not be able to give me all the exact answer, but you should know more or less what it's going to look like. Where does it start and where does it end? Let me ask you that. So in this case, yeah, so it's my input is 4u of t. So it's like there's a switch closing. No.
So wouldn't we start at 0 because it would initially lead tree?
Nope. What have I told you the initial condition is here?
10.
10. My initial condition is 10. Okay.
Sorry, 10.
Okay. So I'm going to start at 10, and eventually, what's going to happen in steady state?
Oh, it's going to reach 0, isn't it? Because eventually, when
almost right, Nathan. Right. What's the final value? So just think of this as a circuit, right? If I had 4-volt source here, right? If I had a 4-volt source, what's the final value going to be? 4 volts.
4 volts.
Yeah. So my final value is going to be 4. I'll draw it like this. What's it going to look like in between 10 and 4? Yep. Look like that. All right. So I know intuitively, and that's why it's important to me always to check my intuition so that I can look back at my solution and say, is that right? All right. I should be able to get some sense of it. Now, Nathan, I said you're almost right. The exponential, the transient response always goes to 0. That means that the total response always goes to the final value. All right. The transient is what I call that vanishing or disappearing difference between the initial condition and the final condition. All right. So I start at the initial 10 and I get to 4, which is the final. Okay. All right. That's what it's going to look like. Let's follow the process. What did I say was step 1?
Set it equal to 0.
Yeah, so I basically go from my non-homogeneous to my homogeneous, which is to say I pull out the input, okay? And so I say this guy is 0.01 dyc plus yc equals 0. Now notice I also changed my y to y sub c because I'm finding only the characteristic solution, okay? Now, let's follow the approach I used both in my video that I posted over the weekend and in what we did last time. All right, so y sub c, I make a guess. Differential equations is all about making guesses that make sense. We always know that our transients are exponentials, right? So we're always going to guess some kind of an exponential. So in this case, what am I going to guess for y sub c?
AE to the negative AT.
Well, I'm not even going to guess negative. I'm just going to guess that it's AE to the, or it's, I'm going to say CE to the ST, because I think in the homework, I set it up as C, like that, okay? And I got to make sure I make the non-trivial solution of C not equal to 0. All right, now, one thing I wanted to point out, because this is relative to the way I asked you to do this, and we're going to look at this example a little bit more carefully, but I write this as CE to the negative T over tau. That's another way to write that. I don't typically put stuff that way, right? But that's one way I can put this, right? So tau, right? When you look at this thing, Yahoo would probably look at it that way, right? You don't look at this generally. You say the circuit or whatever, the system has a time constant. So it looks like from there, you should be able to relate the tau, which is what I think I asked you to put in the problem, all right, to what the S value is, okay? All right, so what do? I guess that, I plug it in. If I plug that in, what I should get is 0.01 SE e to the st times c, all right, times c, plus c e to the st, all equal to 0. Now, I can factor that guy out, and I ultimately get 0.01 s plus 1 times c e to the st equals 0. Now, I said c couldn't be equal to 0 because that would be a trivial choice, and it is. It's a dumb choice. Okay? E to the st, what do I know about that guy? Can he ever be equal to 0? No, he can't be equal to 0 either. So the only thing that can be equal to 0 is this 0.01 s plus 1. So that tells me that s equals -1 over 0.01 or -100. Okay? My exponential better always have a negative term. All right? My exponential better always have a negative exponent. Why? Why must I always have a negative exponent? If you don't
Because
have
it
a exponent,
needs to eventually disappear. It needs to be shrinking.
yep, it needs to, in order to eventually disappear, that number better be negative, right? And if it's positive, that means that some capacitor or some inductor somewhere is building up infinite energy, and you're violating all the laws of the universe, right?
I have a question.
Yeah.
Is that -1, is it always going to be over the coefficient of the beginning? Like that 0.1?
That, no, not necessarily. It all depends on what the equation looks like.
Where did you get that -1 from? So you divide that,
What -1?
that -1 over 0.01.
I got that from solving the fact that 0.01 s plus 1 equals 0. That has to be equal to 0. So that's where I got that from.
Okay.
Right? It doesn't have to be written that way either, right? I mean, the equation could have been written differently. And that's what, like, I could have given you dy by dt plus 10y equals 5u of t. In which case, you know, I wouldn't have a -1 necessarily, but I would follow the same approach. Okay. All right. But I mean, what we just did there, hopefully what I did there shouldn't look too bad. Okay. So at this point, I don't know what the whole transient is, right? I just know that the transient is c e to the -100t. And technically I know it for t greater than or equal to 0, right? This is my y sub c. I don't know c yet. And I can't get c until I've got to my total solution. All right, now it's time for the particular solution, right? So for the particular solution, what I do is I always guess something that looks like the input, because the particular solution basically tells me it's what I call the driven solution, right? So it's that guy that I need to worry about, all right? So in this case, I guess again. So I'm going to guess something yp of t. Now my input is basically a constant. So what's my output going to be in steady state? A constant, right? If I have 5 volts going into an RC circuit, then if I wait long enough, I'm going to have 5 volts on the capacitor. So I'm going to say in this case, I'm going to guess that the final value is going to be B, some constant, times U of t. And what do? Well, I plug that back into the equation. Okay. So I have 0.01 d by dt of B. Now again, what I'll do is I'll say, let's just do this for t greater than or equal to 0. So I can just say times B plus B equals 4. This is what I have for t greater than or equal to 0. What's the derivative of a constant? 0. So I have B equals 4, right? That was not hard. All right. I got that basically my particular solution is 4 U of t. All right. So I plugged it into the equation for t greater than or equal to 0. All right. So at this point, I have that my total solution is that. Okay. So I'm pretty close to being done at this point. So what do I got to do? I got to solve for C. You solve for the coefficients and everything using the initial condition, but only after you have the total solution. All right, only after you have the total solution. So what I'm going to do here is I was told at the beginning that my initial condition was that it was 10 at t equal to 0. So what do I do? How do I solve? What do I do now? How do I solve for c? Yeah, plug in 0 for t. So I have 4 plus c times e to the 0. Right? What's e to the 0 always? 1, right? So I get 4 plus c. So c is 6, right? So at the end of the day, I get this result right here. All right, now what I did was I put some code in here. All right, code. So similar to the way that I would do this in MATLAB. Yeah, question. U of t is a funny thing to define. We say U of t, that's the time at which I turn everything on. So we say U of t is equal to 1 from t greater than or equal to 0. Okay. So it's basically the instant at which we flip the switch. That's a kind of thing a mathematician could probably argue about for a while, but from an engineering perspective, we'll just say at t equal to 0, it's good. Okay. All right. So here's my MATLAB code that I put together to look at this. All right. So I cleared, I do like I should in any piece of code, I clear everything, or at least clear what's relevant. Okay. Then in this case, I said tau is equal to 0.01, my time constant. So I basically said that I know that this guy y of t is also 4 plus 6 e to the negative t over tau, u of t, like that. Okay. And so I looked at this guy and I said, well, that tells me that my tau looks like it's 0.01, right? So my time constant is 0.01, 1 over 100, okay? And so then what I said was, well, I want to plot this guy for 10 time constants. Now, why did I choose 10 time constants? So hopefully you've learned from Yahoo, how long does it take for a transient to die off? Yeah, I mean, so the rule of thumb is that within about 5 time constants, it's equal to 0. And we can look, we're gonna dissect this guy in a minute, but if you look at this, my time constant was 0.01 seconds. And you can see this is actually the transient response only right here, the blue. And you can see that right there around 0.05 is pretty much 0 at that point. So why did I do it for 10, to do it for twice as long just to be able to see it better, all right? So my time vector, notice what I did was, I did it in steps of tau over 100. And we're going to talk more about how I choose those. I always tell you guys what the time vector is. It's tau over 100 or tau over 1,000 or the period over 1,000. We're going to talk more about how I choose that. All right. So the reason I choose it the way I do is so that the graph looks like the way I think it should look. Okay. And I've been telling you what to pick, but we're going to talk more about how you pick it as we go through the next couple of weeks. So notice what I did here. So I made my time vector, okay? Then I made my transient response right there, y sub c, okay? And I said this guy is y sub c. That's my transient response because it goes to 0 when I plotted everything, okay? Now, one of the things that I mentioned in the homework is when I want to plot my particular solution, I used this, and I referred to this guy in the homework there, the ones function. What the ones function does is it generates a vector just containing the number 1, okay? And so what I did was, and I've talked about this guy before, size t, what that does is it tells me the dimensions of the time vector. So it tells me how many rows and how many columns it has. So let me ask you guys this, how many rows does this vector here have? How many rows? 1. All right. Trick question, right? It's just 1 row. Many columns. I don't want to calculate how many it is. We could do it, right? But it's got many columns, but 1 row. So what this is saying is create a vector of 1s that has 1 row and however many columns t has. All right. And so what I then did was I created my total solution by saying y sub c plus y sub p. And I plotted it. All right. For problem Problem 1 on the homework, or sorry, not problem 1, problem 2 on the homework, you would have something that looks pretty similar to this, except in that problem, you would have, I think, a sinusoidal signal, okay, instead of a constant. All right. So this is y sub c. This reddish guy here is y sub p. And then the summation of them is y. Okay. All right. Questions about that? All right. Important thing too, this is the first time I'm asking you to put multiple plots on a graph. Notice what I did here. I said t comma y sub c, t comma y sub p, t comma y. I always have to have the x vector. So when I say x vector, meaning the x-axis vector, then the y-axis vector, then the x-axis vector, then the y-axis vector, then the x-axis vector, then the y-axis vector. Right? I could plot 100 things if I wanted to, but I always have to have them in pairs. The x-axis vector and the y-axis vector always need to be paired up. All right.
I have a question.
Okay.
So if you were to say like do like a linear regression type plot on MATLAB, and like let's say you had like an x1, x2, x3, and then like a dependent y, is that how you would plot that? Like you would do x1, y, then x2, y, x3, y?
You trying to do a scatter plot?
Yeah.
You could. I mean, you saying if you didn't want to draw a line in between them?
Well, like ideally you would want the line, you would want a line, but like just those three independent variables, x1, x2, and xy, you want all those to be there just like against the y-axis,
So
against the same y.
So what you want to have, let's say, it's you just want to see like 3 points like this.
It's like three separate variables, and like they have like in each variable would have like 100 different points.
Well, that's sort of what I've done here, right? So if you look at my t, right? So my t has in this case, I don't know, 10,000 points. My y sub c has 10,000 points. So I think that's what you're asking, right? This guy has, let's I don't know what it is. We can calculate it. Let's say it's 10,000 points. These two things both have to have 10,000 points. The x-axis vector and the y-axis vector better be the same length, right? But the next one here, even it doesn't have to be the same. It could have been T1, and the only thing that matters is that the x and the y that are paired together have the same number of points. But
Okay.
the two x vectors don't necessarily have to have the same number of points.
Gotcha.
Okay. Usually they do, right? But they don't have to. I think I answered your question.
Yeah, thank you.
Okay. All right. So we're going to do second order systems. All right. Now, second order systems, what we have is two energy storage elements. And the critical thing here is, it's kind of what I highlighted. So for first order systems, I only got one energy storage element. I just get an exponential rise or an exponential fall. But when I have two energy storage elements, the strange thing is I can have transfer of energy back and forth between the two elements, right? So if you're thinking about, a first order circuit, energy can come from the source in that circuit, and that's it, right? But in this case, if I look at let's say a capacitor in an LRC circuit, I can get energy from the source and I can get energy from the L, right? So because of that interaction, right, I can get some really sort of strange effects. And I lose a little bit of energy in the process. To me, this line of thinking, 10 years from now, I'll see one of you guys on the street and I'll be, hey, how do you solve a second order equation? You won't remember how to do that. I know that, right? You're not going to remember how to do any of this, right? I know a lot of people who are very successful engineers, and if I put a gun to their head and said, solve a differential equation, they wouldn't remember how to do it, all right? Critical thing is actually probably this intuition about what this means, all right? That's why I talk about it, because it's a lot more important. You go open the circuits book, there's a billion formulas, right, for how you do this stuff. It's not important. What's important is sort of more the intuition of it a little bit. All right, so I want to give a little bit of an example, and Yahoo might have stolen it from me. I don't know if he did or not. But essentially, I think of a pendulum. All right. And in this particular case, what I'm doing is I have the angle of this guy. All right. From the center line. Okay. And so basically, the center line here would be theta equal to 0. And I'm going to pull this guy back. And I pulled him back to an initial value in this picture of 20 degrees. All right. And then if he goes over this way, I'm going to say he gets to negative 20 degrees. Okay. All right. Now let me ask you this. Right now, if I pulled that ball up and I'm just holding it, it has only only potential energy, right? He's got potential. He can't do it. He's not doing anything. He's got potential, right? Now, if there's no friction in this system, what should happen? If there was no losses in this system,
It should just go back and forth between negative 20 and 20 degrees forever.
it's just going to go back and forth. And if I plotted what the angle looked like, what would it look like? It'd be perfectly sinusoidal. All right. Now, I have, again, if Yahoo didn't steal it from me. All right, you guys can go back and look at the full thing and listen to my terrible voice. But basically, what I've done is said, okay, if I let this guy run, and if I let it run, go for it. I gotta find the point at which it's actually doing something here. All right. All right. There it is running back and forth. So when as this guy moves back and forth with no loss in that system, the angle traces out sort of a sinusoidal condition. Now, what happens if I put a little bit of loss in the system though? In other words, let's say I put some friction maybe up into this ball joint. It's going to slowly decrease in amplitude. It's still going to have a sinusoidal variation, right? First, what's going to happen is if I look at the picture, right? Okay, if I look at the picture here, on my first swing, I'm going to swing maybe pretty close to negative 20 degrees. But then as I start to come back, some of that potential energy I had stored up is going to be lost because of that friction, right? So I'm not going to get all the way back to 20 degrees. Right? I might only get to 15 degrees, and then I'm going to swing over here and I might only get to negative 10 degrees, and then I might get to 5 degrees, and eventually I'm going to settle out at 0, right? Why do I know I'm going to settle out at 0? Because there's losses, right? The losses are going to make sure whatever energy was there to start with is now gone. All right, and so hang on, I didn't want to exit that. I think. Where do I have it? Blabbered on for a while. Okay, so I added a little bit of losses, okay? When I add the losses, and watch this guy, so let me run it. All right, so now, if I let this guy run, he's going to get to a situation where he eventually stops, and here's what the angle looks like as a function of time. Now, this situation right here, fundamentally what's happening is I get potential energy when I'm all the way at the top, and it goes to kinetic energy as I get to the bottom. And then by the time I get to the second pass, I basically have less potential energy than I started with, and eventually I've got nothing. Now what happens, what do I call this? What's the term I use for this? Well, yeah, so adding the friction gives me what I call damping, right? As soon as I add losses to a system, the system has what I call damping. All right. So in this case, what do I call this type of response? What kind of damping does it have? Underdamped. All right. This is an underdamped system. An underdamped system is one that oscillates, but has an oscillation that ends. Okay. The previous guy that I had there, this response, if there's no loss in the system, I'm going to call that undamped. All right, not underdamped, but undamped. Okay. Yahoo doesn't really talk about that one, all right? It can happen, and the last problem, problem 5 on your homework, is a real problem where that happens, okay? It's not common in circuits 2, but this is a math class, so I can, or more of a math class, so I can talk about that. It is real, all right? It can happen. This is undamped. Then there's what I called the underdamped. And then there is what I call eventually overdamped, which is that. Now, what does overdamped look like? What would the pendulum's response look like when I did that?
Well, you swing it, and before it would even begin to slide away, it just stopped.
Yeah, so it wouldn't even go around the first time, right? It wouldn't go past 0. So let's watch it real quick. So I'm adding some loss in, and I run this guy. So watch the pendulum here. It just poops right out. All right, he doesn't swing in the negative direction at all. He just dies off. Yeah. Would a Newton's cradle be an exist of an undamped? Not quite sure I know what that is, but we talked about that. Oh, I know what you're talking about. Yeah. Not.
Wouldn't that be
really.
an underdamped system because eventually it stops, but it takes a heckin' long time?
It's a system. So undamped is really hard because basically the universe always has laws, right? So in that system, if you waited long enough, eventually it would stop moving, right? It might take a while, right? But eventually it would stop moving. Yeah, that's basically what it is. All right. Let me wake this guy back up. I shouldn't have closed it. Takes forever to get it back and going here. Come on. You guys in the room can't see what it looks different for you guys. There we go. All right. All right. So now with the second order system, so there's another link to a video here if you want to look at it on your own time, basically seeing how an LRC circuit does the same thing. I start out with no R. That's my undamped scenario. I just have energy storage and then increase the R. And eventually there's a lot of R, there's a lot of losses. And so it just has what we call an overdamped response. Okay. So with Yahoo, you guys have heard those terms before. All right. We're gonna define them a little bit more here, but all right. So in a circuit, Y of t is, I said, always my output. All right. And in this case, in circuits, it could be either an inductor current or a capacitor voltage that you're talking about as your output. All right. But I'm going to call it Y of t. Keep it general. I could be talking about mechanical systems or thermal systems or whatever. I'm keeping it as general as I can here. Right. So we write that equation as a second order system. Right. Y is my output. X is my input. Okay. That's my basic form. And as I write it here, this term B and this term C are constants. All right, all of my differential equations better have constants multiplying the derivatives. Okay, and our total solution has the same exact form it had before with first order. Except what do I know about the Y sub C, the transient response here? It's got 2 terms. Okay, it's got 2 exponentials. All right, those exponentials might be complex, but they're going to be exponentials. All right, so we're going to follow the same solution approach, right? I'm going to start with the transient, then I'm going to do the particular, then I'm going to do my initial condition test to get the total solutions, right? Same basic process. I say this method always applies. I could have a 28th order system and this method would still apply, okay? All right, so the transient solution always solves the homogeneous equation, meaning it always solves the equation that I set equal to 0. So I take the input out. Okay, so x of t is gone here. It's just set equal to 0. Okay, so I always guess an exponential. And we talked at the very beginning last time intuitively why an exponential why that happens. All right, so I guess the solution and then I plop that in. right? So if I plug in c e to the st, help me out with that. I take the second derivative of c. So notice what I do. I always say guess. Always guess, then plug it in, see what happens, right? That's how differential equations works, right? That's how this approach works. I guess c e to the st and take the second derivative of it. I take the first derivative of c e to the st. And then, oh, and there's this b term right here. And I got to be careful. Maybe I shouldn't have chosen c here. I'm going to call this c1. And I'm just going to call it c.
In this
I was
case,
gonna make-
S is negative.
I'm just going to make a really big C. All right. So what happens if I do this and I take the derivative? What happens if I take the second derivative of an exponential like that?
You'll have s squared out front.
Yeah, I'll have s squared out front. So I get s squared, and I'm going to get e to the st to repeat. What happens if I take the first derivative of e to the st? Well, I just get an s, right? So bs, and then plus little c. And I'm going to factor out each term there is going to have a big C e to the st equal to 0. Now, what have we said? What do we know about C? C is never equal to 0, right? And e to the st, what do I know about it? Is it ever equal to 0? No. Okay. So what am I going to end up with then? Well, now, again, the way I'm going to approach this is, all right, S equals, I'm going to do the quadratic formula, right? Help me out with the quadratic formula. S equals what? Whoa.
That would just
Hang
be
Negative b
negative b plus or minus square root of b squared
minus
minus 4 times 1 times c.
all over 2.
Yeah.
All right, given the way I wrote this, right, and there's no a term here, right? So first of all, I know I got 2 roots, and those roots can be complex, right, is the bottom line. And the nature of the type of solution I had, so like whether I got a sine wave or a decaying sine wave or something that's more like an exponential, depends on what those roots look like, all right? So we always have 2 roots, and I guessed e to the st, so my results are always going to look like that. I'm going to have 2 of these guys. So I'm always going to have what I call C1 e to the S1t plus C2 e to the S2t. That's the solution always, always, and always, 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 and forever, right? In Yahoo's class, you're going to learn probably 3 different ways of what they can look like. They all look different. They all look weird. They all have their own set of equations for the initial conditions. But this is what it is always. This is true no matter what kind of damping I've got, right? And so if I know that, it gets a little bit easier for me to say, okay, well, solving any differential equation is the same. I don't need to know all those formulas. It's pretty easy for me to actually just try to do it if I understand this guy from this perspective. All right. So we can go through all those different cases. We're gonna go through it here, but let's look at the undamped case here. So the undamped case, I said the case where, so let me ask you, undamped was which one? Of when I looked at the pendulum, which one did I call the undamped? That's the one you haven't seen with Yahoo, probably.
No loss.
Has no losses. That's the one where what's the output going to look like? It's going to be pure sine wave. Yeah, pure sine wave, right? So in that case, the only way for that to happen is if b was equal to 0. All right. And so what I end up getting is this guy, which means that I get roots that are purely imaginary. All right. Purely imaginary is not really imaginary. It's a sine wave, all right, in the real world, right? Because roots always happen in pairs. And what I see is, in this case, all of these terms are going to be complex. And this guy with Euler's identity is going to become that, all right? We're going to do an example of that in a second, okay? Now, if I get into the underdamped scenario, what's the underdamped scenario? What are the roots going to look like? Are they going to be real, imaginary, or complex? If I'm underdamped.
Wouldn't they be real?
No. What does underdamped mean? Let me ask it that way.
Loss. You lose.
What's that? What's the underdamped response look like? If you needed to describe to me in words what the underdamped response looks like, what's it look like?
A sinusoidal wave that flattens out.
A sinusoidal wave that decays and goes
There it is.
away. That guy is going to be like this. He's going to be complex. Okay. Now, which means he's going to start out this way, and he's going to become something like this. This guy here controls the decay. The real part controls the decay. The imaginary part controls the frequency. And it becomes easier to see why that is as we go through Euler's identity, all right, to manipulate this guy. All right, now, the critically damped, I always say, is a stupid case, right? Because it never happens in the real world. All right, it's mathematically possible. The critically damped case is where you have an exponential, you have basically two roots that are the same. And for something I don't want to talk about in here, basically to satisfy what we call the uniqueness theorem, I basically have to choose another solution. And there's a way of choosing that. But this is something that is so purely mathematical and so non-real that I don't want to talk about it. Okay. In other words, for this to happen, I would have to have circuits with exactly matching components and things. I mean, stuff that really can't happen in the real world. Okay. The other real scenario that happens is the overdamped case, which is where I get two real and distinct roots. When I say real and distinct, I mean real and different. In other words, they're two real numbers, but they're different numbers. Now, let me ask you right now, in any real system, we'll talk more about this Thursday, but in any real system, what always has to be true about the real parts of these roots? What always has to be true about the real parts of the roots that I get? They have to be negative.
Positive?
They have to be negative. They have to be negative.
Sorry.
If the real part was positive, it would grow, and I'm violating the laws of physics.
Right.
Yeah, all the laws of the universe would be violated. They would be violated only for a very brief period of time until everything blew up in the circuit or whatever the system was. Right. It's the picture of the bridge that you go back in the black and white videos of the bridge that's shaken in the wind or whatever, and eventually it breaks apart. Right. That guy has an oscillation that's trying to grow, and eventually he just collapses. All right. So let's do an example. Actually, before I get to the example, I guess I'll talk real quick about the particular solution here, right? We'll look at a particular solution, but essentially the particular solution is I go back to the original equation and I use this undetermined coefficient. I basically guess a solution for the steady state that looks like the input. So if I have a constant input applied at t equal to 0, that's what the u of t means. I apply it at t equal to 0. Then I guess that I'm going to have a constant that also is a solution that is also a constant. Constant in, constant out. Exponential in, exponential out. Sine wave in, sine wave out. Meaning complex exponential in, complex exponential out. Okay? All right, so once I know the two of those, the transient solution and the particular solution, I put them together for my total solution, and then I use my initial conditions to find any unknown constants. Okay, how many unknowns am I going to have by the time I get done? So when I get into this, at the beginning of step 3, how many unknowns do I have? I'm going to have 2. Right? And the two constants in my transient solution are the things I don't know, right? So how many initial conditions do I need? 2. That means I need an initial condition for y of 0, but I also need one for what? dy by dt of 0. All right, so I need 2 initial conditions, one for y and one for dy. All right, so we're going to spend the rest of the class here on an example. All right. So before I jump into the example, any questions you guys want to ask? You're just so mesmerized. It's magical. All right. He's out of your sleep. How's the spider situation going, Nate? Good? Just gonna leave me alone. All right. So I've got, let's say this example, and I forgot to write out here what my initial conditions are. So y of 0 is, I'm gonna jump ahead and I'm gonna jump back. 10, 1. Okay, y of 0 is 10, and dy 0 dt is 1. All right. All right. So where do I start?
I mean the transient.
Transient solution. That's our step 1. So what do I need to do to this equation? So notice what I said. This equation is equal to 2u of t. So before I jump into that real quick, so what is 2u of t? What's that mean my input looks like?
Starts at 2.
2 volts.
Well, you're getting to what my solution is going to look like, right? This 2u of t here means that my input is 2, like that, okay? And he jumps there at time t equal to 0. So this is my x of t equal to 2u of t. So one thing is definitely true. So before I even figure out what the steady state solution is going to be and the transient solution, all that stuff, what is the steady state solution going to look like? Knowing I have a constant input, what's the steady state solution going to look like? Constant. Yeah, it's going to be flat, right? All right. So let's keeping all that in mind. I know I'm going to have some exponentials in here, right? I got to go through and figure out how to solve this. So I'm going to show you how I do this, and I give you in here my code that I use to be able to do this in MATLAB for me pretty easily without ever having to touch any of the crazy formulas, right, that exist in this case. Now, how do I solve this guy? Go get my transient solution. So before I jump into the transient solution, what do I have to do to the original equation here to get my transient solution?
Set it to 0.
Set it to 0, right? Set it to 0, right? So I get that. This is what I call my homogeneous equation. Set it equal to 0. Now, I guess c e to the st, right? Which, I guess that I put it in here. So I guess d squared by dt squared c e to the st plus 4 times d by dt of c e to the st plus 6.25 c e to the st all equal to 0. So I take second derivative. Take a second derivative, what do I get? Second derivative of e to the s squared, what is that going to be?
S squared C
S
e to
squared
the
C.
st.
Yep, you got it, right? So basically what we do is at this point, we usually skip this step and we say, I'm going to end up with s squared plus 4s plus what?
6.25.
6.25 equals 0. All right. So that guy right there, and then I can see I'm going to get 2 roots to this guy, S1 and S2. And to do that, I go to the quadratic formula. All right. But I don't want to go to the quadratic formula because I want to be lazy. Okay. So what I put in here is the MATLAB code that I use instead. All right. So if I have s squared plus 4s plus 6.25, what I can do is I use this command here called roots. All right. What roots does is it finds the roots of an equation for me. And so notice what I did. The last entry. So this guy here is what I call a polynomial of s. Right. And so this first term, if I say this first term here, the 0 order term, I put last. This number 4, I put second. And the number 1, I put first. And notice I put them into square brackets here. All right, I put them into square brackets. All right, and so I say, tell me the roots of that. And there they are. -2 plus 1.5j, and -2 minus 1.5j. Now notice they always come out in, what would you call these two numbers? This guy is S1, this guy is S2. What do I call those two complex numbers? They're the roots of the expression, but what are they of each other? They're conjugates of each other. They're conjugates of each other. Okay? They're complex conjugates. Because they're complex conjugates, Euler's identity is going to turn this into a sine wave. All right? So we're gonna basically, for right now, I've done the transient solution. I got that it's that. Okay? That's my transient. It's two exponentials. I don't know what C1 is, don't know what C2 is, but we can't ever get that stuff until we get to the total solution. All right? So I've got that it's that. At this point, what is this system? Is it overdamped, underdamped, critically damped? Which one is it?
Critically damped? Or not critically, underdamped? Underdamped? No.
Underdamped, right? Which means I'm going to get a decaying sine wave, right? So we don't know what the sine wave is, we just know it's going to decay. All right? All right, so that's that. So now I want to get my particular solution. So I bring back in the 2u of t. All right, now again, if I have a constant as the answer, then I guess, or sorry, a constant as the input, I guess a constant as the answer. Okay, they match up with each other. All right, so I guess that, and so what do I do with my guesses? Well, I plug my guesses in, right? So I say I have d squared by dt squared of b, and I do this for t greater than or equal to 0, right? I don't worry about the u of t. I don't want to think about derivatives of that step input. I do this for t greater than or equal to 0. So this guy becomes the derivative of b plus 4 times the derivative of b plus 6.25 b equals 2. All right, so let's take that. I got a derivative of a constant. What's a derivative of a constant? 0.
0.
Yep. What's the second derivative of a constant?
0.
0. All right, what do I get? I get 6.25 times b equals 2. Reason I call this undetermined coefficients is I don't know what this value is, but I determine it. It's undetermined at the beginning of this step, and then I determine it by the end, right? So I got 6.25 b equals 2. So that tells me that b equals what? 2 over 6.25, which if I did my math right, that should be 0.32. Okay. That tells me if I had a capacitor that I was talking about here in this system, that this capacitor would start at 10 volts and it would end at 0.32 volts. All right. Now, I don't know what path it takes to get there, but it starts at that initial condition and it ends at this final condition. Okay. You guys follow that? All right.
Yeah.
What's
Yep.
yeah. Question?
Oh, no, I was just saying I understood.
Okay. All right. Good. All right. What's my next step here? Put it all together. Step 3 is the total solution, right? So my total solution is at this point 0.32 plus that. Okay. Now, if I had put in Yahoo's circuit formula for this, I would have gotten something I think personally is a lot uglier, right? And if you actually do the math by hand, it is a lot uglier, right? I would have a cosine and a sine, and then I'd take the derivative of it. Derivative of this guy is super easy to take, isn't it? I like exponentials because their derivatives are nice and their integrals are nice. What's the derivative of e to the S1t? S1 e to the S1t, okay? So basically, if I take the derivative of a constant is 0, right? So the derivative of this guy just becomes that, right? Notice I have S1, C1 like that. Now, I was told the initial conditions for this guy were that y of 0 was equal to 10, okay? And dy of 0 by dt was equal to 1, okay? So I took those original expressions here, right? So if I basically say, okay, well, let at time t equal to 0, I have y of 0 equals 10 So 10 has to be equal to 0.32 plus C1 e to the 0 plus C2 e to the 0. What do we know always about e to the 0? It's 1. All right, so those guys are gone. So I have 10 equals 0.32 plus C1 plus C2. Okay. All right. So there's that. Okay. And then for the derivative term, I was told that that was equal to 1. So I have dy of 0 by dt equals 1 equals S1 C1 e to the 0, yep, plus S2 C2 e to the 0, right? Which tells me they disappear. Now what do I have? Two equations, two unknowns, linear equation, I can solve it. Okay? So this was the result that I had right here. Okay? So I want to turn this into a matrix thing because that becomes also easy for me to code up, right? So how should I set this guy up? Well, I'm going to take this 0.32 and move it over here. So that is, all right, let's write it this way. It's 9.68 equals C1 plus C2. And this guy is 1 equal to S1 C1 plus S2 C2. Now we know what S1 and S2 are right now. All right, they're known, they're here. I just don't want to write them out because it's ugly. All right. I'm going to keep it as pretty as I can. All right. So what I'm going to do is I'm going to say I got two equations and two unknowns. I'm going to put it like this: 9.68 and 1 are equal to 1, 1, S1, S2 times C1, C2. You guys follow what I did there? All right. So what I did was I took the first equation and I put it into the first row of this matrix. I took the second equation and put it into the second row of this matrix. And this becomes pretty easy for me to solve, right? Now, one thing I got to be careful about, I noticed this as I was just doing this now. All right, all right, my computer, this should be 9.68. All right. So let me take this guy right here and the best laid plans here. I'm going to paste that code into MATLAB. Okay. So notice, let's look at my code here for a second, right? If I look at my code, I did that roots thing to get my S values. Okay. And then what I did was I wrote it out like this. So this is my, so what I wrote out on the previous slide was B equals A X, like that, right? Or we'll call it AC. That's sort of the way I wrote it, right? Where these are those initial conditions. And then the A matrix is what I wrote right here. So let me do it this way. This is B equal to A times C. All right, we're gonna do more of this, right? But we're recording it, so this will be helpful for you later. All right. So I set that up, and then I do basically this C equals inverse A times B. That tells me what my constants are. Now I'm going to delete this because those constants are wrong. I had the wrong numbers in there. All right, so what are they actually? I just did it in MATLAB properly. So I pasted that code in there. There's my C values. Okay, right there. Now they're complex conjugates of each other. Okay. I see that. They're complex conjugates of each other. And I got time. I can do this. All right. This guy right here. All right. That's my C values are here. Now notice what I had to do. I had to tell me the angle of those numbers, and I had to tell me the magnitude of those numbers. Okay. So I'm going to jump down. I'm going to make a new slide here. All right. So what I saw was that my y of t was equal to 0.32, all right, plus C1 e to the S1t plus C2 e to the S2t, like that. Okay. And what I've now found with these values is C1 is this guy. So this is C1. This is C2. Okay. What this guy is here, this is the angle of C1. All right. This is the angle of C2. This is the magnitude of C1. And this is the magnitude of C2. Okay. So what I see is they're conjugates. So their magnitudes are the same, but their angles are opposites. Okay. So here's how I'm going to write this guy. Right. I'm going to say I got 0.32 times or plus the magnitude of C1. Remember their magnitudes, we just saw that. Their magnitudes were the same. So magnitude e to the, what was the angle? The angle was negative 54. So e to the, and I'm going to do it this way. E to the, so S1 was negative 2. If you go back and look at negative, it was, the roots were defined previously as negative 2 plus 1.5j. Okay. So that's going to turn this into negative 2. And then I'm going to write this as e to the negative j 54, or was it 54.5 times e to the j 1.5t plus e to the j, the other angle, 54.5, e to the negative, or e to, sorry, e to the negative j 1.5 t, like that. All right. Now, we're at the very end here. I'm done pretty much. All right. What do I know? If I have something, when I look at this expression over here that I have right there, if I have e to the j something t and plus e to the negative j something t, becomes cosine. Yep. So this guy is going to become 0.32 plus 2 times the magnitude of C1. So the magnitude was there as 8.3357, whatever, times cosine of what? We're going to end it on this. You guys tell me, what do I, cosine of what? (1.5t minus 54.5 degrees). And that's, that I think is a simpler process. Now I've got the code in here. I'm going to upload this set of notes with the code as well, right? So you guys can see the code that I wrote. All right. And I'll upload this video so you can kind of play around with it. But this is the basic approach that we have to solving these things. All right. And we'll look at more of that. Okay. All right. So with that, I am going to stop and we are done. I can hang out if you guys have questions. Feel free to ask them.